All right, so actually the talk will be presented by Hemant Devarapalli, and I will just take 2 minutes from his talk to connect this presentation to the talk by Sean Rothenberger that will be on Friday, because both talks are on using multimodality approach to blood flow analysis. And as you know, you can measure the flow with phase contrast MRI, with 4D flow MRI, or you can model it with CFD, and both techniques have some limitations and advantages, such as limited resolution of 4D flow, especially in cerebral blood vessels, or relying on assumptions when we do modeling. So when we want to combine modeling data or knowledge about the fluid flow with 4D flow MRI measurements, it is challenging because we don't have a gold standard. And therefore, it's difficult to assess the error of our techniques. But what we do know is that the source of error is different for each technique. And we also know that basically these two or other modalities are representing the same underlying flow. And so I'm showing here an old slide, but it's very appropriate since we are in Nantes, and that's the hometown of Jules Verne. My favorite book when I was growing up was The Infant of Captain Grant. And here we have 3 documents written in English, French, and German with coordinates of a shipwreck. And each document was damaged by the seawater, but they contain the same information. So if you combine them, you could actually read that it's ship Britannia from Glasgow. We also need to have some knowledge about geography. So in our case, going back from Jules Verne example to 4D flow, and here you see this flow in ICA aneurysm, courtesy of Michael Markle and Susanne Schnell from Northwestern. So here, let me go back. We have, and back again. We have 4D flow patterns, and we have some missing information near the wall or in the center of this vortex. So we resolve the dominant scales of the flow, but we're missing some information in the near wall layers. And we hope that we'll be able to reconstruct this if we know the error of 4D flow and we use our knowledge of the flow, such as mass conservation and momentum balance. So the idea here is, if you want to use deep learning approach, we are not training our neural net on a bunch of 4D flow data sets. We actually split the flow into a number of subvolumes, and each subvolume would represent flow in a bent tube, or flow in a pipe, or a vortex, or jet impinging on the wall. And so by training our neural net on those classic simple flow solutions, we would be able to improve our velocity vectors in each subvolume. And then we can combine the subvolume to form the complex flow in the aneurysm. So with that, I now give the microphone to Hemant.
Thank you, Vitaliy. So we've seen that deep learning has been used in so many fields these days, and thanks to the plenary talk today morning, even in this field. So we're looking at one such work by Chen and others where they used ResNet for MRI supersampling or super resolution. And we use this particular network because we think this task is similar to super resolution somewhat, and the network architecture is simple enough and flexible enough. So, and for them, they proved that using 3D data is better than just using 2D slices. And so one thing to note is that their 3D data just has one component per voxel, which is the intensity. But for us, we have 3 components for the velocity, U, V, and W. So to make it work, we split the components into 3 parts, tripling the dataset size, and then we pass it through the network separately. And we see that we get 48% structural similarity. And so next, we do what all deep learning practitioners do, increase the size of the parameters and see what happens. And it didn't really work out. We took a performance hit, But it would make sense because our data set is really small. So the specter of overfitting was always right around the corner. And it seems that quadrupling the size of the parameters, it set us in. And then now that we had some sort of baselines, we tried to use our own architecture. And the idea is that we know that each of the velocity components, even though they are acquired separately, they are still based on the same physical velocity. They're just projections. So now we have 3 parallel paths, and we take all of the 4D data, we split them into each component, pass them through a parallel path, and assemble them back to calculate the error. And we have much better performance. And we think this is the reason is because the network is processing all 3 components at once, so it can understand the intercomponent relationships. So this is interesting because when we compare this to the previous network, it is smaller and still performs much better. So now that we looked at the architecture, let's look at the data set. And so our data is kind of difficult to get because we would need 4D data, and we need the ground truth as well as the measured flows. So instead, we started using synthetic data along with in vitro data. And for the synthetic data generation, we used configurations such as pipes, elliptic pipes, rotating cylinders, and then we added Gaussian noise to it as a start. And then we took all of this data, in vitro and synthetic, split it into 9 by 9 by 9 volumes. And then we further split it into 7:1:1 ratio for training, testing, and validation. So everything sounds good, but now we want to see how it actually looks when we pass in vitro data. So we recorded the in vitro 4D flow from a pipe from our experimental setup at Purdue, and we trained our parallel path network for even longer, 10K iterations, and a better learning rate. And then, so you can see that there's quite a bit of noise at the edges near the walls. And so that's what we're trying to reduce. And then when you look at the network's output, you can see that there is much better vectors now near the walls. So to understand what's happening even better, we look at the PDF plots of each component. So looking at the U component, we see that the spread has been squeezed, so the noise has been reduced. And we see something similar with the V component. Again, the error has been reduced, the spread has been squeezed. But things get interesting when we look at the W component, which is in the direction of the pipe flow. So we have 2 peaks here, which is quite mysterious, and it doesn't really make sense. But when we pass it through the network, we find out that it now follows a nice distribution, which makes sense when we look at the pipe flow. It should follow a parabolic flow path. So yeah, it does seem the network is able to denoise. But so what's next? So I mean, there's no way to cut it. It's still an ill-posed problem. So we did use classic deep learning methods. We used RMS error, for example, as a loss function, and it did help. But now what if we are able to embed our knowledge of incompressible fluids and see how it performs? So for example, divergence, right? So instead of using it as error, how about we use it as a means to train the network itself, and not just using RMS error, but maybe RMS and divergence. So that's what we're working on right now. And apart from this, we are even working on even better estimates of the error, which will be presented by Sean on the last day. So that's it.